Welcome to an overview of the National Groundwater Model of Jordan. The National Groundwater Model has been set up based on the available geological and hydrogeological data and reflects the conceptual understanding of the hydrogeological processes. It comprises all relevant hydrogeological units and aquifers in Jordan, as well as wadis and spring discharge and about 5,000 abstraction wells. It covers all relevant groundwater resources and is available for the Ministry for Groundwater Resources Planning. The groundwater model calculates groundwater levels and flow directions for different aquifers according to available data and common conceptual understanding. It is used to calculate groundwater levels, shown here as groundwater contour maps for the upper limestone at the left and the lower sandstone aquifers to the right. The arrows indicate the different flow directions in each aquifer system. The left image shows the groundwater contour lines for the upper limestone aquifers. The groundwater flow is directed from the highlands east towards the Azraq Depression and west towards the Jordan Valley. The right image shows the groundwater contour lines for the lower sandstone aquifer. They show a different pattern. Groundwater flows from east and south towards the Dead Sea, and the water is here. As seen, the model allows to simulate the lateral distribution of groundwater levels for each aquifer. But it also allows to simulate and investigate the groundwater level at specific observation points. These graphs show examples of observed measurements at specific monitoring wells from 1960 to 2017. Black dots reflect the observed groundwater levels at the monitoring wells. The graph shows a decline of groundwater levels at early times and a sudden change of the drawdown rate at later times. This phenomenon is commonly observed at many monitoring wells, especially in those wells located close to areas where significant agricultural irrigation and groundwater abstraction takes place. An explanation for the change of drawdown is given by an increase of groundwater abstraction in the vicinities of these wells. With the groundwater model, we applied two scenarios. First, the business-as-usual scenario, here in orange, based on the domestic groundwater abstractions from the WIS database and agricultural abstractions derived from remote sensing data analysis that determines the actual crop water demand. Applying this scenario, we were able to reproduce the historic development of groundwater levels at the monitoring wells, including the changes of drawdown rates as described above. The orange curve shows a good fit with the observed data and follows the observed trends. The second scenario, we applied a scenario with controlled groundwater abstractions according to the groundwater bylaw, the blue curve. This scenario indicates how the groundwater level situation would improve by applying limited controlled abstraction rates. The difference of both curves indicates the impact of the unknown or illegal abstractions in these areas. We have seen that the groundwater model is capable to reproduce the historical developments of the groundwater levels. And therefore, the model is also capable to predict future developments of the groundwater levels. The following animation is showing the simulated future drawdown starting in 2017 until 2050. Declining groundwater levels are shown as colored areas. The animation shows how much and to what extent the groundwater levels are declining in future. It clearly indicates those areas that are impacted most dramatically with a drawdown of up to additional 100 meters. These are in the north near Mafraq, east of Madaba, and the Wadi al-Arab area. Areas with an intensive agricultural land use or impacted by the Wadi al-Arab wellfield. Having seen that we are able to predict future groundwater level decline, we now want to explain the consequences of these falling groundwater levels. First consequence, falling groundwater levels result in wells falling dry. This map shows the situation today. Red crosses mark dry wells, while blue dots mark productive wells. The following sequence shows that the number of red crosses is increasing. More and more wells are falling dry or become unproductive. A second consequence of falling groundwater levels is a reduction in groundwater availability. This graph shows the overall abstraction rates from 1960 to 2017 and its simulated prediction until 2050. The red line is the sum for all aquifers. The other lines represent the abstractions in the individual aquifers. The graph shows that groundwater abstraction is steadily increasing since 1960 until today. Starting in 2017, constant groundwater abstraction rates have been assumed, the dashed line. But the simulation is showing an overall decline of groundwater abstraction by 13%. This decline is a result of a reduced productivity of wells due to falling groundwater levels and due to the wells falling dry and therefore not producing any groundwater at all. The falling groundwater levels result in a reduction of groundwater availability. A third consequence of falling groundwater levels is an increase of groundwater production costs. Falling groundwater levels result in a higher pump lift and therefore in higher energy costs, namely electricity costs. A brief calculation of production costs for domestic wells in the A7B2 aquifer with average assumptions for electricity prices and pump efficiencies stipulate almost 25% additional costs only for pumping due to falling water levels in future. This represents a substantial financial volume that will have to be raised in future. To conclude, a groundwater model is available as a tool for assessing groundwater resources and for predicting future developments and planning options. It allows the quantification of available groundwater resources and can be applied to predict future developments. A significant future groundwater level decline is predicted by the model simulations. As a consequence, these falling groundwater levels result in a reduced groundwater level availability, b. more and more wells that fall dry and need to be deepened or replaced, and a significantly higher production costs for pumping the groundwater. For more details, please visit the Ministry's website